Hello, my name is Jim Cullafello, and I'm the Vice Dean of Academic and Student Affairs at the Ira Fulton Schools of Engineering at Arizona State University. It's my pleasure to welcome you to our National Academy of Engineering Grand Challenges for Engineering Speaker Series, hosted by ASU and sponsored by the Kern Entrepreneurial Engineering Network. This engaging speaker series will focus on the 14 Grand Challenges for Engineering in the 21st Century. Esteemed speakers from across the nation will be sharing their expertise on these grand challenges and answering your questions. We are proud to be a part of the NAE Grand Challenge Scholars Program, preparing graduates to address these challenges. It's my pleasure now to introduce Dr. Ramakrishna, the Director of the National Academy of Engineering Grand Challenge Scholars Program Network, to share his welcome.
Hello, my name is Ramakrishna and I am the Director of the National Academy of Engineering's Grand Challenges Scholars Program Network. The NAE Grand Challenges for Engineering, identified in 2008 by a committee of the National Academy of Engineering, are 14 critical global challenges for engineering in the 21st century, united by the mission of continuing life on the planet and making the world more sustainable, more healthy, more secure, and more joyful. The Grand Challenges Scholars Program, inspired by the NAE Grand Challenges, reflect the rapidly evolving nature of engineering education. The goal of the program is to prepare engineers who not only have the necessary technical skills, but also the cross-disciplinary knowledge, entrepreneurial spirit, the global multicultural perspective, and a sense of societal mission needed to meet the global grand challenges facing humankind in the 21st century. As of November 2018, 65 institutions across the US and around the world have implemented this innovative educational program, and nearly 100 are getting ready to join the consortium of GCSP schools. We at the National Academy of Engineering are thrilled that Arizona State University has taken the initiative to organize this series of presentations that will highlight each of the 14 NAE Grand Challenges and provide this valuable resource not only to its own students and faculty, but to students and faculty from around the world. On behalf of NAE, I'd like to thank ASU and the Kern Foundation for making the presentation series possible. I'm eagerly looking forward to following how this series impacts and inspires the next generation to create solutions to our society's most daunting problems. Our best wishes for a successful series, and thank you very much.
Hi, my name is Ryan Muth. I'm a lecturer at the Ira Fulton Schools of Engineering, and tonight I'm going to be the moderator for this event in our Grand Challenges Speaker Series. I'd like to welcome you and thank you for coming tonight. Tonight, Dr. Nathan Siegel will speak about the grand challenge of making solar energy economical within the theme of sustainability. After his presentation, you'll have the opportunity to ask questions, and I'll be asking some of my own. I'm very excited to welcome and introduce Dr. Nathan Siegel. Dr. Nate Siegel is an associate professor of mechanical engineering at Bucknell University. He has over a decade of research experience developing concentrating solar power and fuel production technologies. Recently, Dr. Siegel was a team member on the SunShot-funded Falling Particle Receiver project and also advised a student who designed and built a novel high-flux solar simulator used for thermochemical reactor testing. Prior to coming to Bucknell, Dr. Siegel worked at Sandia National Labs in the Solar Technologies Group on projects including high-temperature receiver development, solar fuels, and molten salt heat transfer, fluid synthesis, and testing.
Great. Thanks a lot. Hi, everyone. Thank you for, I almost missed the chair there. Thank you for coming to the presentation and to the organizers for inviting me to come talk with you today. So I'm going to talk about the grand challenge associated with solar energy, which is to make solar energy more economical. And I'll get to that in a second. But first, the title. I I'm basically just going to lead in with the statement that low-cost solar energy is already here. So that was one of the goals of making it more economical. So then the question is, what's next? Hopefully I hit the right button. Oh man, let me hit it again. There we go. I was thinking forward went that way, but it goes that way. Okay, so when we say make solar energy economical, I think that usually means one of two things. We either make it less expensive. We can see that the cost of solar electricity has been coming down, these two charts right here. Or we make it more valuable. We do things to make it so that we can get better use out of it. And for solar energy and other variable generation technologies like wind, more valuable means that you can use it when you want to use it, including at night or during periods when the resource hasn't been available for some extended period of time. So when the grand challenges were first initiated back in 2008, the cost of solar energy was relatively high. It was economically cost prohibitive, even at the utility scale. If you look at this chart here, you can see what's happened with utility scale solar. Back in 2008, 2009, it was more expensive even than the most expensive conventional generation, which would be a gas peaker. But since then, it's come down to about 4 cents a kilowatt hour at the utility scale, which makes it cheaper than any other conventional generation technology, at least any of them that I have on this chart right here. So this includes the major ones. I'm not going to say that I got all of them, all right? So including things like coal and gas combined cycle. And I also have a line on here for solar tower, which is another type of solar energy generation technology that uses concentrating solar power. And even that's coming in at a position that makes it competitive with some of these other more conventional approaches. So the costs have come down since that 2008 Grand Challenge was initiated, and deployment has increased. So I think that the combination of these two things should make us pretty comfortable to say that solar energy, at least at some level, is already economical. So if you look at deployment, it ramped up massively. In 2016, we had a great year. And then tariffs happened. It slowed things down for a little bit, but not as much as people thought. And it looks like things are going to come back. But this probably won't continue forever for reasons that I'll discuss here in a few minutes. In the CSP world, and CSP again uses something like this system here, which is a central receiver, focuses light from these mirrors to a heat exchanger up here, where a fluid is taken out of a tank, heated, and put into another tank. And that heat can be stored for up to 12 hours in some of the new commercial systems and used to drive a conventional power cycle, like a steam turbine. And so CSP also enjoyed a lot of growth, and it peaked around about 2014, 2015. And the systems that are going on now are actually a little bit different than what was installed in the past. And I think that's one of the reasons why we see a little bit of a slowdown. The emphasis now has gone to installing systems, CSP, that include storage. So now you see more power towers, whereas in the past you saw troughs with no storage. Now you have power towers with 12 hours of storage, like Crescent Dunes in Nevada. And I think that's a really important development, and I think that one will continue into the future. So economical includes two things, cost, and it includes this utility factor. Where can I find opportunities to reduce costs? And for utility scale PV, DOE publishes charts that look like this that show you, here's where we are today. Nominally 7 cents, and that depends on where you put the system. Okay, so solar, the cost of solar is driven at least in part by where you locate it. If you locate it in a really bad solar area, it'll never pay itself off. If you put it in Daggett, which is pretty good for the US, it's even cheaper than 7 cents per kilowatt hour. So when you think about cost projections and cost data, where those systems are matters. Anyway, there's some room for improvement in module cost. We can take the module cost down a little bit. And this is true at the utility scale. We can lower the balance of system. Increasing lifetime is a really big one. So you pay the same amount of money up front, but now your system lasts twice as long. So that's a much better investment for you. And then lower O&M. So what does it take to actually keep the system operating at peak performance? All of these things combined are what's needed to get to, or at least what's thought to be needed to get to the 3 cent per kilowatt hour SunShot target for 2030. Now, take this with a grain of salt. The last SunShot target that DOE had, the industry vastly outperformed. They hit the target for solar energy costs well before DOE thought they were going to hit it. So I like to think that this is even a pessimistic view of where we could be in 2030. In terms of CSP, the thing that is limiting CSP in terms of its ability to achieve really, really low costs is the heliostat field. So you saw those mirrors. Mirrors are made of glass and steel. Glass and steel costs a certain amount of money. You can figure out sort of where you need to be on those costs in order to bring your overall system cost, levelized cost of energy down to a level here for the target of 5 cents per kilowatt hour. But this target is higher than the PV one for the reason that it also includes 12 hours of storage. The PV target does not. And that's pretty important. So CSP, DOE is essentially saying we're not interested going forward. We want the targets to be for systems that have storage. And that's where the value for CSP is really seen. But if you want to come up with a really, really good idea in CSP, figuring out how to do those heliostats for less than $50 per square meter, that would be the good idea. So this is my off-grid solar power system that a student built for me a few years ago. $3 a watt, parts sourced completely on Amazon, right? So what I want to, this system gets about 15% efficient. It's about 15% efficient. If I somehow doubled the efficiency, now I would be paying $1.50 a watt. Essentially, if I double the efficiency without adding cost, that's a major win. The entire system gets cheaper. And I think that's something that we're going to see people focusing on going forward. When you talk about, when you look at it from the Department of Energy's perspective, they have these lines on this chart. These are all 3 cent per kilowatt hour levelized cost lines. And what this is saying is that what you get from efficiency, if you're down here, let's say you're on this yellow line, the baseline, and you're at 15%, that means you can afford to pay 15 cents per watt for your module. If you somehow make the efficiency go up to 40%, you can now afford to pay almost 40 cents a watt for that same module. So it gives you flexibility to increase costs elsewhere in the system. But the biggest win is if you increase efficiency without increasing those costs. If you come up with ways to improve the efficiency of the module that do not add cost to the module, okay? So there's a lot of room for improvement. Over here on the left is an overlay of the solar spectrum, that's the white outline, with the portion of the solar spectrum that's turned into an electron when in a single junction PV cell using something like silicon with a band gap of 1.1 eV. And what this is showing you is that these photons over here don't have enough energy to actually produce an electron in a hole inside the material, so nothing happens. These photons over here have enough energy. They actually, a lot of them have too much. And this white area up here is the excess energy that isn't utilized by the cell. But the point I want to make is you can fill in a lot more of this space if you design, let's say, a better device. Over here is a chart that's a bit dated. It's a few years old. Right now, the best conversion efficiency for a commercial unit is somewhere upwards of 22% for one of SunPower's modules. The best research cell is on the order of, I think, it's either 27.6 or 28%. And that's getting really close to this SQ limit, which is sort of the limit of efficiency for a practical, or I'm not going to call it a practical device, a real device. It includes some loss mechanisms that aren't included in an ideal case. The best you could do if we use, well, it's not the best, but you could do better if you go to a multi-junction module where you have, instead of just a single semiconductor junction that's converting all that energy, you layer them where you have different band gaps in that structure. And if you do that, you can get to much higher efficiency. So my point with this slide is this. If you're going to increase efficiency, perhaps one way to do it is to look beyond these single junction modules to try to make an inexpensive multi-junction module. We have multi-junction modules now, but they're cost prohibitive, at least unless you're using them with a concentrator or something like that or in a satellite. So if you could have one that was less expensive, you'd essentially double the efficiency beyond where we are today. And I think that would be a big win if it didn't add a lot of cost. For CSP, the way to increase efficiency is broadly thought to be by increasing temperature. So right now, the push from the Department of Energy and everything that they're funding for the Gen 3 projects in CSP is to go to 700C and above. But 700C is kind of the magic number for them. because that works for this power cycle here, which is the supercritical carbon dioxide Brayton cycle. It's a gas turbine that essentially has a working fluid with the properties of a liquid. So it takes very little work, for example, in the compressor. So it can be relatively efficient at low temperatures. So a lot of DOE effort is being expended to support this cycle, which works really well for this red region here, which is a power tower. So that again is the sort of the platform that we're moving toward. But when you talk about temperature, it's one thing to say increasing the temperature increases efficiency. That's true for the power cycle, but it's not necessarily true for the system. So what I'm showing here is what happens if you take this number, which is sort of your conversion efficiency. This goes up with temperature. And this number here, which represents the losses that you incur in a CSP plant when you try to collect heat at high temperature. And those scale with T to the 4th in a purely radiative sense. There'd actually be convective losses on there as well, which can also be significant. But what happens is this results in sort of a maximum. So we're operating in this region for concentration ratio here, somewhere between 600 and 2,000 on a power tower, which means that our best case performance is in the vicinity of 1,000 or 1,100. And that's one of the reasons why DOE is focusing on this sort of 700 degrees C target, because that gets you pretty close to that sweet spot, right? There's also some other implications here. When you get too hot, you have to stop using things like stainless steel that we all know and love, and you got to get in nickel alloys and ceramics that are really expensive. So there are additional costs incurred to going a higher temperature, but this is something that I think is, generally speaking, a broad focus of CSP. There are other opportunities within CSP to do good things, and I think that one of them has to do with collection losses. This is sort of a waterfall diagram, it's really big, of the entire CSP system. Right up front, just getting the light up to the receiver costs you between 20 and 40% of your energy. Just on that loss right there. Usually it's higher, the loss is higher for towers because the tower incurs something that's called a cosine loss. The mirrors aren't pointed normal to the sun. They have to split the difference between where the sun is and where the tower is. And that gives you a relatively large loss. Things like parabolic dishes don't have that. But because you're giving so much up here, I think that represents a really nice opportunity to do some innovative things. And I think there are two innovative things that you could consider. One is to do a better job with the optical efficiency of a power tower. The other is to do something like a parabolic dish, which is a very optically efficient platform, and figure out how to get high temperature heat off of that dish. So the dish can run with a concentration ratio of 5,000, right? So it can go efficiently to higher temperatures, but it has to move in two axes. And we have no way to get that high temperature heat off of that dish and take it somewhere like to a central power block. And if we can figure that out, again, I think that would be a major innovation for this field. Okay, so now I'm going to go into the second part of my talk, which is to discuss the value side of the making solar energy more economical topic. And part of that involves making it more dispatchable, making it available when you want it. And you might think, if you've thought briefly about this, one way that you can do that is with storage. That's the easy one that we all can kind of wrap our minds around pretty readily. But there are other things that you can do to make solar more dispatchable. You can make, for example, the grid a lot smarter. You can make it more flexible. You can do things like demand side management. There's a lot of opportunity in this space. And I'll talk about a couple of these things here in a minute. But I just wanted you to see that dispatchability is more than storage. So now I got to talk about the duck. So some of you may have seen the duck curve before. Anybody seen this? Okay, good. So this is actually not the one from Cal ISO. This is one that some colleagues of mine made for a paper that we were working on. But essentially this shows you one of the issues with increasing the amount of solar energy that you're putting onto the grid and not changing anything else. And I'll tell you how that works. So essentially, as you add solar electricity, what it means is that the rest of the power plants that you already had on the grid, they have to dial back their generation. So throughout the day, in the middle of the day, depending on how much solar you're bringing on the grid, you have to dial them back. And there's a limit, though, to how far back you can throttle these plants. And a lot of people will call that must-run capacity, and that might be this dashed line right here. if you start to approach that dashed line, you can't turn the power plants off anymore. The nuclear plant doesn't want to get turned off. So that's just not going to happen. Gas turbines, no problem. So once you get down to this point, you start turning off your solar or your wind. And so now you've paid for that thing and you're not using it. So there's no incentive. If you know you're near this, you're not going to build more solar and you're not going to build more wind. So there's two things that you can do to tame the duck. Oh, I forgot to tell you about the other problem. The other problem is the end of the day when everybody goes home, turns on their stuff, and the sun goes down all at once. Well, over like a 2-hour span. Then you need to ramp up at 4 gigawatts per hour. Everything's got to come back online, right? That's not fun for the grid. So what you can do is you can make the duck a little bit skinnier by taking some of this energy and storing it. And then you can shift it over here and feed it back to the duck in this area, essentially reducing that ramp rate. So that's the value of storage. The other thing you can do is make the grid more flexible. You can take this line and decrease it, right? So now you can have a fatter duck before you run into problems with overgeneration. So those two things both need to be done. So lots of ways to make it flexible. The easy ways, the low-hanging fruit are things like this. Just improving the way we do business, the way power is moved around on the grid. Improving infrastructure, that seems like it makes a lot of sense. So maybe we don't have enough capacity, for example, to handle massive increases of solar electricity throughout the day. You can do things to increase ramping. This also increases flexibility a lot because these systems can be completely turned off and there's not as much of a consequence as there is for something like a Rankine plant. And the most costly thing, but perhaps the most useful thing, would be to develop energy storage. And there's been a lot of talk in the news about batteries getting cheaper. Tesla invented, he came out with the Gigafactory, everything's getting really inexpensive, right? $120 a kilowatt hour, maybe even less. So what is the consequence of that? Well, here's something. So right now we're at $179, right? That's dollars per kilowatt hour that you go and you pay for the battery. And that battery, these costs are a little bit misleading because that battery only has, let's say, a cycle life of several thousand cycles before you have to replace it. So you'd actually need a slightly different cost measure called a levelized cost to get at this in great detail. But the point I want to make here is this price is already competitive with gas peakers. So you already see people building battery banks for the grid that could look like a replacement for a gas peaker. And you probably see that continuing into the future. But then you might ask, can we just do it all with batteries? And the answer to that is no. This chart right here shows you what happens when you try to do it all with batteries. So when you have a battery and you use it a lot, you pay a certain amount of dollars for that battery and you divide it by the number of cycles, and then you get a number that's like dollars per cycle, right? So if you're using the batteries a lot daily, that's great. But if you want to replace all of our power generation with solar, then you have to have enough battery or enough storage so that you can go weeks without any reasonable amount of sunlight. Or you can deal with the fact that in the winter, the solar resource in the northern hemisphere is way less than it is in the summer. That's called seasonal storage. So you need to have excess capacity that you only really cycle once per year, right? And because you're not cycling it a lot, its cost becomes huge. You build this massive infrastructure and you hardly ever use it. That's a problem. And that's one of the reasons why, unless you can come up with a battery that is literally as cheap as dirt, and that might not even be cheap enough, you're going to struggle to do 100% renewables with something like solar and wind. So what happens next? So that, what I hope that I've shown you is some amount of the pressures and the developments that are happening right now around solar energy and renewables in general. And if you think about all that stuff, you can kind of get a feel for where the field might be going, but it's still really difficult to know exactly where things are going to end up. So instead of trying to answer this, I want to pose this question to you. So if you assume that we're going to vastly overshoot our 3 cent per kilowatt hour DOE 2030 target and we end up at 1 cent per kilowatt hour, I don't want to say it's too cheap to meter because that might make some people recall other technologies that are supposed to be too cheap to meter, but it's pretty cheap. Right? 1 cent per kilowatt hour, but you only have it for 6 hours a day. Okay? So I'm assuming here that solar is going to keep going down, but we're not going to figure out large-scale storage. So what are you going to do in that situation? What new technologies, what new things will we start doing when power costs us very little? Right? This is something for you all to consider, because to me, this is probably the most interesting question in renewable energy right now. So I think that there's a lot that you can do. I don't know if any of these are gonna happen, but let me just throw a few things out there. There are possibilities of making fuel, right? You can make fuel from the sun. You can do it thermally. You can do it electrochemically. If you have electrons, you have all kinds of flexibility. Electrons are 100% exergy, right? It's nothing better. You can do things like desalination with solar energy. These are just sort of illustrations of these concepts. You can do things like charging your EVs during the middle of the day, or perhaps making things like metals and stuff like that. But the caveat is, most of these systems have not been optimized for this sort of intermittent operation. And I think that's one thing that, to me, is very interesting, is trying to think about the things that we currently use electricity for and adapting them to this sort of paradigm where we have the electricity, it's low cost, but we only have it for 6 hours a day. All right? So I think that's all I have. Again, thank you very much for inviting me and for listening.
Awesome. Thank you, Dr. Siegel. That was a great overview of the challenges of solar energy and a lot of opportunities for people like you to innovate and provide value for a lot of people that could take advantage of these new technologies. For the rest of the time, we're going to give you guys the opportunity to ask questions of Dr. Siegel.
I guess I can stand up for this.
I
didn't know if we were standing up or sitting down. I'm going to stand up.
Well, we're going to sit down here in a second. Just about his topic or anything else that you're curious about. If you want to ask a question, you can text it to 505-552-2377. That's also in the program, so you can text there. If you're watching online, you can send questions directly through the video feed and the YouTube live chat. And we'll do our best to answer as many questions as possible. But while you're sending those, I've got some questions for Dr. Siegel right now.
Okay.
Okay. So, besides the necessary technology development for this kind of stuff, are there other impediments to adoption of these renewable energy sources?
I think the biggest impediment to continued sort of implementation of variable generation on the grid is that duck chart, really. I mean, you can keep doing a little bit more for a while, but there have been study after study that basically show once you get to a certain level, it just becomes problematic. And once overgeneration starts happening on a regular basis, then the economics of solar are somewhat compromised. So I think that enhancing grid flexibility is certainly something that we're going to have to do a better job with going forward.
Yeah. And probably related, in Arizona and probably in some other cities as well, we've experienced some pushback from the local power companies for the home solar installations and sort of the sellback programs and stuff like that. They're saying things like, we're pushing the cost off to people that aren't doing solar generation. Is that part of that problem?
I think that's related, but that actually gets into another topic called grid defection. And so in grid defection, what happens there is if the price you pay for power is high enough, it actually becomes economically advantageous for you to add a battery system to your solar energy system and essentially not use the grid very often. You maintain the connection to the grid so that you can have it in the event of an outage or like a period of bad weather or emergency or whatever, but you don't really use a lot of energy. And so what happens is now the utility loses your revenue, right? And they have to push those costs onto their other customers that pay that rate, or they have to come up with some other way to sort of disincentivize that kind of behavior. There was a study, I can't remember where I read it, but already in Hawaii, it's economically advantageous at 28 cents a kilowatt hour to just do this, to defect from the grid essentially.
Wow.
And I think that's going to continue to happen for residential scale.
Wow. In some cities around the world, I saw an article in Japan, and there was a partnership with Toyota and Honda, I believe. They're encouraging people to use their electric vehicles as backup systems for power generation. Is that a reasonable approach, or?
I think it could be, but so it depends on how much backup we're talking about. Because fundamentally your vehicle has to get you from point A to point B. So you could use it in that context as a backup, but you can't draw it down too much because then you won't be able to use it as a vehicle. So I think there's a case to be made for using vehicles in the context of grid services, for example, where the utility could essentially maybe decrease the charge rate or source energy from that vehicle and put it back onto the grid as a way to sort of manage things. And they could compensate you for that. And that will probably, I would imagine, happen. But even if you did this with all the vehicles, I don't think that it would ever solve the problem that we see in the duct chart, which is a much more massive problem, especially when you consider that you just aren't going to over-design the batteries that much in a vehicle. It's a pretty big battery already just to get you a relatively short distance to your office or wherever.
Right. I've seen some sort of energy storage schemes. Like one was they literally just push a train up the side of a hill during the day, and then they let it drag a cable down the side of it. Are those more efficient, or are they all suffer from the same kind of?
No, so that's basically if you can't do pumped hydro and you have a train and a hill, that's what you do. So this is, I think, called Aries is the name of the project, and I believe it's either in Nevada or California, but they basically have a hill and they fill these trains with rocks, and during the day they drive them up a hill on sort of a cable arrangement, and at night or whenever they need the power, they let them fall down the hill and it spins a generator to produce power. And I think that's great, but I would encourage any of you to do this. You can do the calculation for potential energy and see how much weight you have to lift, how high to equal, let's say, a megawatt hour. And it is a surprisingly large number. Pumped hydro is the biggest grid scale energy storage technology that we have because reservoirs can be massive, right? You can store a lot of volume of water, and water is pretty darn dense. So that makes sense. To do this in a constructed system where you're having to build trains and rails, I think it's a tougher value proposition, but it does work.
Do you see anything on the horizon that would help do that seasonal storage, or is that sort of an open problem?
I would say that's an open problem right now. I don't know. I mean, there are a lot of really old papers that you can read from the 70s and 80s and the start of the solar research industry in the US where they looked at these things. And I would encourage anybody that's interested to do that. But I don't know if there's anything that I've seen that I would say, oh yeah, that's it.
Awesome. So how will the adoption of renewable energy change the job landscape in the US?
I think what it does is it creates a lot of opportunities for people to work in the renewable energy sector. And I think that includes scientists, it includes engineers, it includes people who can develop and run businesses, who can find opportunities to get these technologies out there. I hope to see more manufacturing in the US, and I hope that would be one consequence of doing more renewable energy in the US, but I don't know if that's in the cards or not.
So you're a mechanical engineer, right? What other disciplines are involved in these kinds of systems and the work that's being done, and what kind of work do they support?
I would say all of them. I mean, I showed you that one chart that showed the kind of this grid of the future, right? So obviously you have electrical engineers to develop power systems, power hardware. That's one of the main costs in current utility scale and residential scale systems is the power electronics. You have civil engineers who have to develop all of the infrastructure, including installing transmission and stuff like that. Mechanical engineers also have a role in system analysis. Obviously for CSP, that's a pretty heavy mechanical engineering type field. And I would argue that, when you look at residential scale solar, for example, the biggest single cost are the soft costs. It's customer acquisition, I think, is one of them. The other costs are related to installation. So we need people who can think creatively about how to actually develop business models that can reduce some of those costs so that it makes it more affordable for people to install solar energy systems.
Great. Besides the stuff you sort of outlined today, are there any other technologies or trends that you're super excited about?
So I don't know. That's a tough one. So I did my master's degree in nuclear fusion, and I have not given up hope, right? So I'll say it right here. I love nuclear fusion. I think eventually it'll save our bacon, but obviously it's still 40 years away.
Right. So, perpetually 10 years away.
I see a lot of innovation in that space now. There's a lot of these startup companies that are purporting to have new technologies that may get us there. And I don't know. Maybe I'm just being unusually optimistic, but I would really like to see something like that. I think that we can solve a lot of the problems now with a really not very sexy approach of just changing the way we live and conserving more. So I don't know why this never gets talked about. I guess energy technologies are super sexy, but we could do a ton if we just changed a few things that we do and tried to get our per capita energy use in line with other countries that have a quality of life similar to ours, like Europe, for example. I don't know that the sacrifices would be great, right? I don't think they would be. It's just a matter of sort of a collective will to do that. And I think that that's something that we should really think hard about.
We're right into the audience questions, and I think that was a great lead-in. As an expert in the field, what do you think people or society will most likely do if we do end up reaching that low-cost energy but only have it for 6 hours a day?
That's a tough one. I think that the idea of enabling the electrification of the transportation system will happen. It may be now when you buy an EV that you end up with, let's say, 2 battery packs instead of 1. So you can charge one at home, you take the other one to work, you plug it in at work. And so during the day, you can increase the overall demand on the grid, but it's all going to charge these batteries. And maybe if the PV isn't there, they just don't charge. Something like that. I think that you can get into creative models that involve electric vehicles that make use of this intermittency, but do it in a way that doesn't necessarily compromise the rest of the grid operations. So to me, that would be something that will probably happen given the popularity of EVs.
Mm-hmm. Is battery storage necessary for the growth of solar?
No. So you can do more. Battery storage isn't necessary. Storage may be necessary, but you can do a lot with other things to improve flexibility before you have to really come up against this barrier where if you're not including storage, you're kind of out of luck. I think that ultimately to get really, really high levels of renewables, you need to have some way to store. But I think that where we are now, we can still put a lot onto the grid just by doing things a little bit differently in terms of this flexibility argument.
Mm-hmm. Do you see like the sort of smart appliances and things like that fitting into that?
Absolutely, because what that allows the utility to do is better regulate demand, right? So they can turn things off when they know that they have a period approaching where they're going to have a shortage, and they can avoid rolling brownouts and stuff like that. So I think that can make a difference, certainly. And even things like, having refrigerators that can overcool and then essentially sit idle for periods where that power is going to be needed for other things. Yeah. So I think there's a lot of opportunity in that space that we're just not doing because we don't have to right now.
So kind of as an American culture, do you think people are going to be cool with giving that kind of power over to the power companies to choose when to turn their fridge on and things like that?
If it was worth their while, they would, and if it didn't compromise their lifestyle. Mm-hmm. So I think those two things, you got to have some sort of an incentive.
Right. And
it probably doesn't have to be much. I can teach a class right now and offer students 1 percentage point of extra credit, and they'll do almost anything for that 1 percentage point. It's like this psychologically, just getting a little bit of something. If you don't really have to do anything for it, you're going to go for it. Mm-hmm. Well, why not? But I think it's important then to develop technologies that sort of fill that niche where you're doing something good, but you don't actually feel the pain. Mm-hmm. And that's what people are really afraid of, is feeling this pain. And that's why I think conservation is typically thought of as something that is just really difficult.
Awesome. For this 1 cent per kilowatt challenge, it seems the best choices would be those activities that have high total cost derived from electricity and low relative capital, which you would want to maximize your utility. One example is mining Bitcoin or similar computational activities. Do you see a lot of room for this and other kinds of digital usage?
So I'm going to agree with the first part of that statement. In terms of mining Bitcoin, that's actually really interesting. I suppose it depends on sort of how Bitcoin does going forward, right? Is that going to be something where there's a lot of value and money to be made? I don't know. I mean, I don't know much about Bitcoin. That might be a better thing for you to answer.
Well, on the flip side, you see companies like Google and Amazon building data centers right next to hydroelectric power plants because it's cheap, right?
Mm-hmm.
They have all this centralized offsite computing, right? Would you see maybe that growing as well because that's their principal operating cost? Possibly, but then you still have the issue of it's only available for 6 hours a day. Right. So then what do you do for the rest of the time? Because if when the 6 hours is up, you end up having a ramp to get to bring that power back online to keep that server farm running, then you haven't really gained much. Right. You can't like bank. So you have to believe in the entire paradigm, which is this cheap power and only 6 hours. What are you going to do? Yeah, good call. Are big corporations slowing down the field of renewable energy in exchange for profit? It's tough. I mean, probably big corporations will do anything, really, I think, to generate profit. And I think that that's what they're supposed to do. I don't know that there's a conspiracy necessarily to do that. And I think that corporations, if they're smart, will diversify what they're doing as they see trends shifting in different directions that are maybe outside of their current business model. So I don't know. I'm not a conspiracy theorist in that particular area, maybe in some other areas. But so I don't know. I mean, I think that probably there is some of that going on, but maybe not as much as people think. What do you think about Elon Musk's Tesla solar roof? Is that enough to power an entire house, or is that? You mean the one with I mean, he's got the power pack too, right? The 5 kilowatt hour or whatever it is. I think this question is referring to the solar roof tiles. I mean, I guess it could be, but it depends on a lot of different things. So the roof tiles are going to be, obviously they work. You have to have enough roof space, and your roof has to be oriented properly, and you have to be in an area with lots of sun, and you have to have electricity rates that make it affordable. In the end, it comes down to an economic argument. If you have an installer come out to your house, they will show you some really simple calculations that they'll do to tell you what your payback period is. It's not hard. My dad had it done. He put a 7 kilowatt hour system on his house, 7 kilowatt system on his house, and he was paying 28 cents a kilowatt hour. So for him, his payback period was something like 6 years in Southern California. Wow. So yeah, I would say that, and that was for pretty efficient stuff. Even if you had a less efficient module, if the price point is low enough, yeah, it's going to pay. The warranty for things is like 25 years for most of them. So I would argue that it's probably a good investment. Awesome. For CSP, the complex tracking systems have kept the cost high. What are your views about it? I don't know that it's just the tracking system. The tracking system is part of it. It also has to deal with just when you think about what these reflectors look like, there's sort of a mindset that we want to have mirrors on the order of 100 square meters. And so when you build a mirror that big, it ends up being a pretty big wind target. And you don't, it's not the tracker that's solely the problem, but also the drives that have to hold this thing because it has to point very accurately to reflect that beam of light. And so you have big drives, and maybe you have a lot of field wiring. You have a lot of things going on that require infrastructure that we don't necessarily need if we're a little bit smarter about how we do it. And so I think that there have been innovations in tracking. We have heliostats now that you don't have to go out and manually aim. They can auto aim. You can put them out in the field. They don't even need to really know where they are. They have targets that they can go to and detect their position. So the tracking electronics and all that is not a whole lot. The drives, that is a big expense. You can design heliostats more elegantly to reduce the cost. It may cause you to have to bring them down in size. I don't know where that ends up, but that was the business model of eSolar, right? They had these 1 square meter nominally heliostats. And that was I thought a pretty good approach. I don't know why they aren't still doing that, but So are the storage challenges you describe mostly in the developed or industrialized nations, or how do the challenges, these kinds of challenges, differ in developing communities?
So I think in a lot of ways, I think that the attitude that people have towards reliability is different in different countries. So if you were to tell me that I had to live for 3 hours a day without any power, I would think that that was just completely unacceptable. If you were to tell that to somebody who lives in, I have a student who is from Nepal, and he said that we do this all the time. We used to fill a wheelbarrow with car batteries and go down to the micro hydro plant to charge them up and bring them home, and then we would have light. And so that, in developing countries, the mindset is different. Having any reliable electricity, if you know that it's going to be there for these 4 hours, you're willing to work with that because it's better than what you have now. Wow. So there's probably a lot of opportunity in the developing world to do things that would make a huge difference to people who are used to thinking about electricity differently than what we do here in the U.S.
There's talk of pumping water back up into Lake Mead to use it as a battery. How will something like that impact solar?
That would be a great way to basically take some of that excess generation and store it. You could do that. Mm-hmm. So you have to essentially have another pump that is similar in size to the turbines that are already letting the water out of Hoover Dam, and then put it back, because I don't think those turbines run in reverse, right? I don't think they're built that way. So you'd have to do that, but sure, that could be done. But then, don't you need that river water for something, right? That's the Colorado River. So
yeah.
I don't think you can run Lake Mead as a closed system. That would be the challenge right there.
Yeah.
Glad we came to that.
California would have something to say.
I was just about to suggest getting rid of the Colorado River.
Do you think Apple's campus is entirely solar powered?
I have no idea, but probably not.
Yeah.
It can't. I don't think it can be.
Yeah.
Right? They got to have something to run them through the night. Right. They might say that you can buy solar electricity and pay extra to say that your energy is coming from some mix of renewables, but I think that there's always going to be some carbon-based electrons floating around in that mix.
Mm-hmm. Good call. All right. This one is a little bit out of left field.
Oh, okay. Great.
Yes. So there's been some recent breakthroughs in room temperature semiconductors. Like they got it down to 1 degree Fahrenheit, but under extremely high pressures, like 20 gigapascals. Do you see crossover technologies like that influencing your field in the near future?
Yeah, I think the superconductors would be great, obviously, for transmission and associated losses there. That could make a big difference in our ability to move power from where it's being generated to where it's needed, even over long distances, potentially across the country. Other technologies that I think are kind of interesting to watch, or things that are similar to the superconductors, would be thermoelectric materials. So there have been advances in thermoelectric generators where before they were kind of in this 3% conversion efficiency, and now they're getting up to 12, 14% conversion efficiency. And these are solid state devices. And to me, that's kind of neat, because when you look at where our energy is wasted in this country, a lot of it is sort of this low to mid-grade heat that we could do more with if we had cheap technologies to harvest that resource. And I think that something like thermoelectrics could be something that we could use to produce even more electricity and make ourselves generally more efficient on an energy basis.
The thermoelectric systems, are those solid state?
Yeah, this would be like a little, it kind of looks like a CPU, right? A little chip.
Peltier junction.
Yeah, the Peltier junctions,
yeah.
Right.
I was reading something about concentrated solar at a really small scale with using Stirling engines.
Oh yeah.
Is that
yeah.
on the roadmap anywhere?
Well, that was on the roadmap. So that happened back in 2000. I don't know when they were around, 2006-ish. This was a company called Stirling Energy Systems. Did a lot of work to develop dish power systems that were at 25 kilowatt electric power level. And they did a ton to improve reliability of the Stirling engine, to improve the manufacturing costs of the dish and the engine, and they installed a 1 megawatt plant in Arizona, not too far from here, that ran briefly, and then the company went bankrupt and was bought by a company in China, and I have no idea what happened to the technology.
Oh, wow.
So the problem with Stirling is that it got into a situation where it was competing directly with photovoltaics. Photovoltaic costs were falling rapidly. Neither technology had storage. Why would you build a dish Stirling system when you could just put up more quickly at less cost a PV system? If neither one has storage, neither one has an advantage, right? So that's, I think, what happened. Do I think the Stirling engine has potential? Yeah, I do, especially for microgrid and distributed generation. But the Stirling engine is a reciprocating engine. And so that means that there's only so much power density you can get out of it. So you can take a Stirling engine and you can make it a little bit bigger, but the engines that we have in our cars, right? You're not going to get, 100 kilowatt, 200 kilowatt. Those are, and that's a liquid chemical fuel combustion. Stirling engine, you actually have to push the heat in across an interface, and that's really hard to do, and scale up to high power density. So to me, a more interesting proposition that's related to the Stirling would be something like what's called an Ericsson cycle. And an Ericsson cycle is like the Stirling cycle. It's an ideal cycle, and it's what you get when you take a gas turbine, which is a Brayton cycle, and add multiple stages of intercooling and multiple stages of reheat. So mechanical engineers in the room should just love that. And I think that is an opportunity going forward to do a much more efficient power cycle that would work really well for what we can do with solar energy, at least for CSP right now.
Great. So we're getting near to the end here, and I'd like to do a call to action similar to how you ended your talk, asking other people how to get involved. So you've inspired some people here probably to take action. How can students or others get involved, and what can they do to contribute to addressing these challenges?
I think that a good start is participating in something like the Grand Challenges program. Doing research or becoming more interested in the types of topics that we talked about today is a good first step. But the other thing that you ought to do is just become more informed about the energy landscape as it currently exists. It's really important to have sort of a high-level view of how things work and the limitations, the advantages, the disadvantages of different technologies so that you can make good decisions going forward. You're going to end up doing research or working in an area that's probably going to be relatively specialized. But if you have a broader picture of what's going on, I think you'll be better positioned to be successful in whatever it is that you're going to do. Don't become too stovepiped, I guess is what I'm saying.
Well, that's all the time we have for tonight. Please watch our website for future events in the NAE Grand Challenges Speaker Series. And again, please thank Dr. Siegel for a great, inspiring talk.
Thank you.